Hi, this is Bruce, and welcome to my Rocky Mountain Labs. And today we're going to take a look at this absolutely beautiful Philips PM6622 DC to 80 megahertz timer counter. This thing is in fabulous shape, obviously been taken very good care of. There's no scratches in the case. The aluminum, the escutcheon's all in beautiful shape. The stand, the display, just a gorgeous piece of equipment. We're going to give you a quick tour of it. The counter timer is capable of measuring frequency, period, time intervals between two signals. Does a ratio between signals on A and B. It can count on A with the start and stop either being manual or being controlled by the B signal. It has various resolutions on just about every function. We're able to read signals right down near the DC. I've never seen that actually myself until I worked with this unit and was able to put in a signal. We're going to demonstrate that in a moment here. We have trigger levels that we can set. We can vary the sensitivity of the unit. We have push button sensitivities. There's a built-in check function for the unit. AC and DC coupling. We can combine both channels together, or we can keep them separate on the separate COM. We can take a look at the trigger on the upward slope or on the downward slope. So just about everything you'd want. We can freeze the display using the display time. That all figures into the gating. Right now we're feeding in a 10 megahertz signal from my rubidium source, and we're reading 10 megahertz right to the hertz. And if I go down to the 10-second time, we'll see in a few seconds. We're going to give it 2 rounds just to make sure we get a good reading. The time base that's in the unit is the second best time base for the series. It's a temperature compensated crystal oscillator, TCXO. Has some good features to it. And as we see right now, we are reading 10 megahertz down to a tenth of a hertz at the moment. So let's go ahead and run through some functions on it and see what we think, huh? All right, at the moment we are set with a resolution of 100 hertz. That's our highest range. And we're going to take this thing up to beyond its maximum spec value, which is 80 megahertz. Right now we're feeding in 10 megahertz. And I'm going to dial select from this PTS 500. I'm going to dial select some frequencies and we can take a look at it. The PTS is coupled to my rubidium, so I'm not going to do much better in terms of frequency. All right, we're at 100 megahertz right now, which is already over its spec. We're going to go to 110. Well, there's 110 right there. I just had to dial up a little bit with my voltage output. So with a little bit of sensitivity sacrifice, we're reading 110. If we go back down to 80, we should have no problem. Yeah, let's take ourselves down into the next range. Pick up a little bit more resolution. So as you can see, 79 to 80, we can go 1 hertz. There's 80 megahertz right there. So no problem on the high end. Let's now take it down to the low end, and we'll demonstrate about the DC signal. Okay, well, we're in AC mode, AC connection, and we are currently reading a 5 hertz signal coming from this HP3320 signal synthesizer, and we're reading 5.1 hertz at the moment. Now if I put myself into DC mode, give it a moment. Okay, there's 5.0. Now, I don't know how many of you ever looked at 5 hertz on your frequency counter, but let's go ahead and take her down to 1 hertz. Yeah, we got to give her a few seconds. We're in a 10-second time mode right now. So we want to go through 2 cycles. First one was interrupted when I made the change in frequency, and the second one will settle in about where the frequency is. Right now we're reading 1.1 hertz. Give that gate a moment to blink. Alright, just blink. So I'm reading 1.1 hertz right now. Let's go ahead and try 0.5. Alright, we've got 0.5 hertz coming in. 0.5. 0.5 hertz on the display. So I doubt any of you probably have ever read a half a hertz. But let's take her down to 0.2 hertz. 0.2 hertz. Wow. Well, how about 0.1? We're doing that good. Alright. I just saw the blink, and there's 0.1. 0.1 hertz. That's pretty spectacular. I've actually never seen that, but seeing is believing. There it is. And I know I'm generating that, so just really interesting. Okay, let's move on. Okay, when you're reading extremely low frequency signals with this type of a counter, if you stayed in frequency mode, you're generally just going to see a very small resolution. Like you're going to get 1 significant or 2 significant figures. Like when we had 5 hertz, it read 5.0. When we had 1 hertz, it read 1.0, or when we went to 0.1, you had 1 digit on the entire dial, and that was 0.1. So if I want to read more accurate, get more resolution into my reading, then I want to read the period. If you want to read the period on this meter, you read it on channel B. And we are DC coupled again. We are on the 0.1 millisecond range, and we are reading 10,001.9, well, 1.2 milliseconds. 10,000 milliseconds. Well, 1,000 milliseconds would be 1 hertz. And in period, 10,000 milliseconds would be 0.1 hertz. And we are reading 0.1 hertz. So getting 10,000 is expected. So go ahead and do the math if you like. 1 over 10,002.4. And you get an idea just how accurate that generator of mine is over there. Alright, and if we wanted to increase our resolution, we would dial up to 0.1 microseconds as our minimum resolution, and it's going to take longer. The gate time is going to take longer in this case, but we're going to get a whole lot more resolution. So like we get 10,002.1 1441, for instance. And if we go beyond that, there is averages we could take. Like this would be an average of 100 readings. I don't want to wait that long, do you? But, okay, so we don't have to wait for 100 periods where the period is for a tenth of a hertz. 1 hertz has 1 second. A tenth of a hertz has 10-second period. If I had to wait for 100 of those, I'd be waiting a long time. So it's not really, the averaging is not really meant for super slow signals. So in this case, what if we took a look at a kilohertz? And we have 1 kilohertz dialed in right now. Well, I can take 100 readings off of a kilohertz, and I can do it every, tenth of a second, something like that. 10 times a second. So it really doesn't take very long for me to build up a count. Right now, we're getting a one average of about 1 million nanoseconds. Well, 1 million is 10 to the 6th, the nanoseconds 10 to the minus 9th. So I'm getting 10 to the minus 3rd pulses out as an average, and that's a millisecond. So 1 millisecond, a period of 1 millisecond would be a 1,000 hertz, period of 1,000 hertz. So we are reading 1,000 hertz to 6 significant figures on average. I could turn this up, but let's go ahead and let's dial this up to, let's make it 100 kilohertz. That's 0.1 megahertz up here. That's 100 kilohertz. So, all right, let's say we go and try and read 10,000. We'll do an average of 10,000 of those periods. And what I'm getting right now is an average reading of 10,000.00 nanoseconds. Well, 10,000 nanoseconds, that's 10 to the 4th times 10 to the minus 9, gives me 10 to the minus 5, which would be 0.01 milliseconds, which would be 100,000 hertz. If I have a period of 0.01 milliseconds, I've got a period of I've got a frequency of 100,000 hertz. And that's what this thing is telling me on average. So my averaging's working. If I went to 1 million counts, it's going to take longer to take this. We're going to wait one more 10-second period here, and but we should get our maximum resolution. All right, so we're getting 9,999.999 nanoseconds. So we had 10,000 a moment ago, so we're reading 100,000 hertz to 3 significant places at least. All right. So let's take a look at the ratio next. Okay, I've got myself hooked up so that the signal on channel A comes from the PTS 500 up here, which is producing an 80 megahertz signal. And right now I'm reading 79,999.9 kilohertz, which would be 80 megahertz. Then on channel B, I've got I've got a signal coming in from my 3320B, and right now it's 100 kilohertz. So if I had 80 megahertz over 100 kilohertz, that's 80 times 10 to the 6th over 10 to the 5th. Well, that would be 80 times 10, which would be 800. And I'm reading right now 800. You can see it blinking between 79 and basically all nines to 800, 799 to 800. And that's doing a ratio down here. I can increase my resolution by raising my number of averages, I guess. And yes, I got 799.99953. So now what if I reduce this to 10 kilohertz? That's what we just did. Instead of 100, I should see my display now rise to 8,000. And I think I'm going to have to, there we go, reduce my average. There we go, 8,000, 7,999, and all nines to 8,000. So it's doing the ratio just fine. And I could do all kind of squirrely ratios I might like to do. But it gives you the power of comparing an unknown to a known and getting a ratio and then figuring it out. I could choose to count A, but if we're going to do that, it'll be more interesting if we can see the counts instead of seeing them fly by. Watch them happen at a reasonable speed. Let's reduce this to, say, 10 hertz. Okay, what we've done now is we have on channel B, we have 1 hertz coming in from our 3320B. We're connected on channel B by DC, so we're going to get our low frequency reads accurately. We see that we're strobing on our trigger level. And we're feeding on channel A from BTS 500. We're feeding a 600 kilohertz signal from that unit. And so we're allowing channel B to turn on, and that tells us how long we can count and then turn off. And I've got B as a start-stop here, so we're starting with a signal and then stopping. Right now we're reading 599,921 to 600,039, so around 600,000 pulses that we count for every 1 second strobe on B. And that's what we expect. We expect 600,000 pulses that we're going to count. Let's see if we can find a slower signal to count. Okay, what we've done now is we've fed a signal from that Ray Caldana oscillator that's up there, and right now we're feeding in 100 times 10 to be about 1,000 hertz. So we've got 1,000 hertz coming in. So we've got 1,000 pulses per second, and we have a 1 second time period that we're measuring from B on. And we are counting 1,000. Now, go ahead and display one of these little auxiliary features. There's a memory button on here. What it's doing right now is it's remembering the end of every count and displaying it. So I see only the ends of the counts. If I want to see the actual counting take place, I can take the memory out, and you can actually see the counting up. So the counting function on A is working fine too. There is an input on the back that allows you to connect a switch, and you can manually switch in the start and stop feature. Actually, that switching might involve a high and low voltage that you switch in. I'm not sure. We'd have to look at the manual on that, but there is an input in the back that allows you to manually control this. Or you can do it as I'm doing it, using another signal generator to act as my time base. Okay. Well, so I've given you an all-around view here of this PM6622. It's one of my favorite units. The Philips series of 66 units are fabulous. Somebody's going to be a very happy owner. And I'm wishing you luck on your bidding, and thank you for listening. And see you next time.